All right, so this is matrix / data approximation video 2. So the goal of this video is to get some algebraic evidence of what we saw in video 1. So if you didn't watch video 1, definitely watch it first. We'll say specifically to get algebraic evidence that the spread, if we like, of the data is what the SVD captures, if you like, or represents, or whatever word you like. So to do this, what I want to do is I want to look at the SVD calculation again. I want to revisit it, say something more technical about it, not the original calculation, but how the matrix multiplication works out, and make some statements that are based upon that, right? So to do that, observe the following, right? When we have an SVD, this is what we have. Now here's the deal. If you go through, and let's actually give these some dimensions. So we'll say m by n. This is m by m. This is m by n. And this is n by n, just for reference. Now here's the deal. If you go through this and you actually write down what this matrix calculation is, in other words, if you give all these u's and v's entries and all the s's variables, this is what we get. So the actual matrix calculation. This isn't obvious. You sort of have to write these matrices out in a really sort of rudimentary way. But the basic idea is that when you calculate the first vector in A1, right? So this A1 bar is the very first column of A. Right? This turns out to be the following product. So it becomes a sum of, let me write a couple of steps and I can say something about it. There'll be one of these for each column in A. Now the K in this case is with K singular values. So the K here is the minimum of m and n that we saw before. So what happens is there's a similar line for each other A, but let's take a look at this one just for a second. What this is saying is that the A, this column of A, this is the first data point, if you like, of the matrix A. This is a linear combination of the U's. And the weights of those linear combinations is this product. Now, the V's are all pretty small. The V's are all between 0 and 1, right? Because those come from the unit vectors. But so it's the S's which are the bigger values, which are the meaningful values, right? So basically what we see when we see this is that the U's are like building blocks. They're a perpendicular basis, right? So we see what's happening here is that the U sub I, these are forming a basis for Rm, and each column of A, like in this specific example A1, but each column of the matrix A is a linear combination of that basis. So if we kept going, like if we wrote another line, right, this is what we'd get. The second column of A, it's still built out of the singular values, but now slightly different V's, but the same U's. Right? So we have this trend that continues. The only thing that's changing here is the V values. This should go down to, oops, this is 2K, sorry. And if we keep going down to the very last one, which is A sub n, This is S sub 1 V sub N1 U sub 1 plus S sub 2 V sub N2 U sub 2, and so on. So it's the same pattern. In that, again, we see that this is true for every A. In other words, every column of A is a linear combination of the U sub i's. So this is what we see. Let me summarize sort of some things we've just said, but then some additional things. Is that again, each column of A is built from the basis that's made up of the U's. That's the first thing. Right? The second thing is, because the S go in decreasing order, remember the S1 is the biggest one, so because S1 is greater than or equal to S2 is greater than or equal to ... all the way down, the highest S's carry more weight. Right? In other words, the U1 is more important because it's connected to the S1. So we see, let's say, the relevance, or the importance, if you like, of the UI go in decreasing order. Because each UI is multiplied by Si and then some V. But it's this S that's giving the priority, if you like. In other words, if the S is large, that U will have more relevance. Now this actually tells us something more that's interesting, which we're going to talk about and then go back to the picture, is that if we take the sigma, right, so if we look at all this calculation that's done, all this messy stuff right here. So if we were to go back to the original sigma matrix, right, so if we took that sigma matrix, and suppose we set some, say, S sub I, some particular one to be 0, to get a new sigma. So I want to call this new guy sigma prime. Right? And redid this multiplication. A, or not A, let's say, well actually we could say A prime, if we like, is U sigma prime VT. Suppose we did that. So if you think about what happens, right? So if we look back at the calculation for a second, I'm going to mark some things on the left. So suppose we set S2 to be 0. So what that does is that gets rid of this and this and this and all those S2s that run down there, which means it gets rid of the relevance of the U2s. It eliminates the U2 direction. So what happens is, if we set some Si equal to 0 and get sigma I, and we redid that, the resulting points, or let's say the resulting data, has thrown out the corresponding U sub I direction. So to see what we mean by that visually, let's take a trip back to the first example. I'll write it, and then we'll take out each S independently. There are only 2 of them, and we'll recalculate, and then we'll look at the result. Right? So we'll do that on the next page. So here, let's revisit our first example. This is what it was. Okay. So I'm going to pause this while I fill this in. So let's take this. This is our A U sigma VT. So we'll make 2 notes. Suppose we set S2 to be 0 to make a new sigma prime. So sigma prime, basically what I'm going to do is I'm going to go up to here and I'm going to delete this. I'm going to make that a 0. Then if we recalculate, in other words, I take exactly the same U, I take, in other words, let's do this, let me write it this way. I create a new A. I take exactly the same U. I take the new sigma prime, which is this. This is what we get. So again, let me pause and fill this in, bunch of digits. So this is the result. So I'm going to plot these, but before I plot these, what I want you to do is just compare two things. I want you to compare these against the originals. They're pretty close, right? Like they're not exactly the same, but the values are more or less approximately similar, right? So let's see what happens if we plot these. So let me pause this and try and get this as good as possible. So what we've got here so far is the original picture. So the 4 blue dots is the original data. The pink lines are the original vectors. So nothing new has been added. Now, this is what happens if we add these new points. Right, so I'm adding 3.81, 1.49. Right, that is about here. Actually, I forgot one pink line. This was the U1 line. We also had a U2 line. I want to keep that U2 line there. So for the next one, if we plot the 1.21, 0.47, we are right here. You might be able to see what's happening here. Then if we plot the negative 1.74, negative 0.68, that's here. And then last but not least is here. So what you may have seen has happened, and it kind of makes really, really good sense, is because we've deleted the S2, by deleting the S2 right here, we have removed the U2 direction. The U2 direction is the short direction, right? So what happens is all the points are then shifted so that they only have a U1. In other words, the points lose the U2 direction. So you can probably guess what's going to happen if we set S1 to be 0. So here, if we set S1 to be 0 to make sigma prime. So then what we're doing is we're doing A prime, which is the same U. Now we have a 0 here, a 1.312. That's the guy that's removed. That's the guy that stays, is the U1 direction. So let me pause and fill this one in. So here we've got, I did two things. I did the new A prime calculation. What is this? Right there. And then I redrew the original data yet again. Right? So now what's going to happen is we plot these. We plot 0.19 and negative 0.48. And that comes out to be right here. So this is appearing, let me mention some things as we go. This one that's appearing, this comes from the 4-1. This one is being, we're losing the U1 direction. It's going all the way back to U2. So it's like doing a perpendicular projection but sideways. So then when we do the next one, the negative 0.21, 0.53, that's this one right here. That's the one that comes from the second data point. Right there. And then there are two more. There is this one. Again, this is not the perfect picture. And this one. Those points are what comes from here and here. So here, the points lose the U1 direction. So we can imagine if we had more dimensions, we would have multiple senses of direction, and we could pick away at those directions one by one, or we could eliminate the big directions, the small directions, some of the small directions. And this is what we'll do when we start to do data approximation, like really hardcore calculations, is we can get rid of certain amounts of data, because what's happening here is we're simplifying the data, right? Like if we look at this particular example while it's still on the screen, in a sense, if you were analyzing the first set of the set of data that we were given, the 4-1, 1-1, negative 2-0, and negative 3-2, you could say that, like, well, maybe the short direction is just noise, and the primary direction is the U1 direction. So you've sort of done some analysis there. You've looked at the direction of sort of primary spread. If you wanted to simplify the data, you could say, well, look, if that's noise, if the small direction is noise, let's just get rid of it by deleting the 1.312 and recalculating the matrix. And so this is sort of if you think about things like data compression is all about eliminating small properties of the data that you don't need. That's when image compression kicks in. Handwriting recognition is all about looking for the most important features. In other words, deleting the least important features. And so this is why this idea of the singular value decomposition becomes so present everywhere, because it has this built-in mechanism for looking at the most important features of the data in a linear sense like this, and looking at the least important features of the data and being able to pick those out and recalculate immediately. So let me stop this video here. What I'll do in the next one is I'll do a couple things. I'll do a little bit more technical details so that we can understand what do these numbers mean. Specifically, let me circle a couple of things here. We know what the vectors mean now. We know what the u's mean, right? These guys were good. Right? We can see the evidence that these provide the directions of significance. But these numbers, right, what do they actually mean? Because they mean something visual. So I'd like to revisit that, and then we can sort of do a summary and put everything together.